Hi everyone. For this code along, we're going to look at an adjacency list for a graph. And the idea behind this is you have a set of vertices and you create a list for every vertice on the connected edges. Now let's go ahead and take a look at this first and try and visualize it before we code it, because visualizing graphs are critical. And often for a graph, the first thing you do is you start with a whiteboard, or you start with some sort of way to go ahead and take a look at everything. So we'll go ahead and take a look at the whiteboard, and we will go from there once we have taken a look at the whiteboard. So assume I have a fairly simple graph. And this graph has 4 nodes, and because I'm a computer scientist, I'm going to start these nodes at 0. So we have node 1, which is a 0, and then we have node 1, 2, 3. So we have these 4 nodes here. And we connect the nodes, so from node 0, we go to 1. We're going to do this as a directed graph, and from node 0, we go to 2. And then from 2, we go ahead and go back to 1. And then the only way to get to 3, we actually do this from, actually I'm going to flip this around. From node 1, we go to 2. This would be more interesting if we do it this way. So node 1, we go to 2. And then from 2, we go to 3. And we can assign weights to each of these. And this is how much it costs to go from node 0 to node 1. It gives a cost of 5. And to go from 0 to 2, we have a cost of 3. So maybe node 1 is way off there a bit farther. And to go from 1 to 2, it's only a cost of 2. So, and to go to node 3 from 2, we go ahead and have 7. So each of these have a cost. And the idea is we say, okay, we have 4 nodes, so I'm going to go ahead and create an array or some sort of data structure, but array is very doable, that each matches up to these 4. So we have spot 0, spot 1, spot 2, and spot 3 for the 4 nodes inside this array. And then for each location of the array, I'm going to create a list of nodes. And each of these nodes contain, or just say a list of edges, and each of these edges contain information about what's connected. So from spot 0, I'm going to have an edge of 0 to 1, and the cost is 5. I'm also going to have from 0 to 2, and the cost is 3. So notice I have this list where it all stores in here, and each element connects to the next one, so each element is connecting down the line, very similar to a linked list. For location 1, we have only one connection from 1, and that's to 2, so it will be 2, and the cost happens to also be 2. Or maybe I'll make the cost 3, or whatever we end up making the cost, we have the balance here. And then in location 2 and so on down the line, we're slowly building these chains where each one matches up with that location. So let's keep this in mind, and we'll code this structure. We noticed I said we have a node, so we're going to need to make sure we have a node structure that has the vertex that it's going to, and it has the weight. I also probably would like to have a structure that maintains this whole array. It could be an array. Honestly, there's other things you can look at for structures, but for now we'll go ahead and stick with array because it's a simple mapping between the original vertice because we can map it across the thing. Or there's other things that we can look at as we do this for the different mappings. But those are 2 structs we're going to need to look at, and we'll slowly build up the list from there. Now let's go ahead and get out your IDE. As always with code alongs, you want to have your IDE open, you want to try it out, you want to pause, you want to go back, you want to participate by engaging, by working through the code yourself. And often when we're coding quickly, you may say, hey, wait, that's coded awfully quickly. And that's fine. Then we can go back and fix some things. So I've put in the standard things. This tends to be my standard blank C file. We have the IO, we have the lib, and then we also have the main, which just returns 0. We'll fill it in as we go about it. But what I want to go ahead and start with is I'll go ahead and start. I mentioned it's going to need a node, so let's go ahead and build a node. So we can go ahead and type def struct node, and this node will be int vertex and int weight. Now I could also call this an edge. I use the term node, but honestly, edge would be a good name for it. Either is fine, and then we say here's another edge that we're going to keep track of, or the next thing down this list. And to make my life easy, instead of having to type out struct node every time, I'm going to say struct t. I also made a comment that we are probably going to want a structure to keep track of the entire graph, and that is really just going to be how many number of vertices are there. It'll make our life much easier if we keep track of that for when we do loops. And then we'll have node t, and since this is a list of these structures, it's going to be adjacency lists, and it's going to be graph t. So these are our two main structs that we have. As always, with a struct, when the first thing you do is, it's good to set up a function to go ahead and create it. Node t, and then we'll go ahead and say create node, and it's int v, which means which vertex is the edge going to, and int how much is the cost of moving down this edge. Now this idea is going to be a directed graph. You could do it undirected, and there's different ways to set it up, but we're going to be looking at this more from a directed standpoint. T, and it's a new node, equals malloc, size of node t. And we say new node. We're going to go ahead and start with vertex equals v, and then new node, weight equals weight. And then, of course, the next one, we don't know yet when we're creating this, so we're going to set it to null. Then we return our new node. Now let's take a look at our graph. We're going to go ahead and create the graph. And the graph takes in the number of vertices. Sorry, it's doing that number of vertices. And for this new graph, we're going to say graph t equals graph. I'll start equals malloc. And we're going to say num vertices times the size of node t. Let's go ahead and graph t. We're going to be doing the next one down in a second. So we're actually saying size of graph t. So let's create the graph. And now we can say graph num vertices equals malloc. And it's going to be num vertices times size of node t star, because it's a pointer to each one. So we have this array of nodes. And then we're going to say for int I equals 0, where I is less than num vertices. Depending on the C++ version you use, this isn't always required, but it is a good habit. We're going to actually set everything to null to make sure we do have the empty values in there. So we can say, all right, here's our list. We're going to set it equal to null. We're going to return the graph. Now, whenever you create something that has a malloc inside of it, so you're creating this object, you need to malloc inside of it, it's really good to create your free function just so you don't end up having a memory leak later. So we can go ahead and say void free graph, and it takes in a graph t star graph. Then we can say, all right, first let's free the inside information. Int I equals 0, while I is less than graph num vertices. Hey, this is becoming nice that we have that in here. And I++. Then we can say, all right, so we have this. Now we're going to say, all right, let's grab the node. The first node is going to be the first one on it, but we have that node, current node. We'll just say current equals graph. That's going to be the adjacency lists I. Then this is a list, and ideally we want to loop through every item in the list and free the item. So we're saying, going to say, while current does not equal null. So keep looping until you're at null, which means since we're saying not equal to null, the very first one is null, well, then we just skip past that. If for some reason we are skipping items in the list, really shouldn't, because ideally it's the total number of vertices, but we have that. But inside of it, we can then say node t temp equals current, just to make our life easier. Then we can say current equals current.next. So we're saying, all right, we're going to store the current one inside a pointer and hold it, but we're going to grab the next one to make that current, so then we can free temp. So we've kept track of it, so that way current is still going, but we can go ahead and free temp. And now that we've gone through the whole thing, we can free graph adjacency list, since that was one of my mallocs, and we can go ahead and free the graph itself. So I've gone through and I've created this structure. For every single malloc, I end up having a free that I've set up, since I can go through, okay, we have the 3, we have the 3 there, hey, we're good to go on that. So we have this different mallocs that we have. And then let's go down into my main, and just to make sure, because it's really bad to code a whole bunch and never actually do anything with it, we're going to go ahead and say, all right, we're going to create the graph that we represented before, the one that had 4 vertices. So we're going to say graph T graph equals create graph with 4 vertices. And come down here and we're going to free graph, and we're going to go ahead and free this graph as the last thing we do for our memory. And just to make sure it is working how we think, I'm going to go ahead and cd into my dev. cd into d colon cdynl. Of course, now you see my directory structure and how I have things set up. Dev, website, and it's C, and it's my code samples. All right, I also created a graph directory, which this is all under, actually cd c graphs. Now, in my case, I actually want to be in Linux because I code everything on Linux, so I've now started the Windows Linux subsystem, and now I can go ahead and code this. So let's clear this. I'm going to do ls, so I have this here and a few other things that I've been working on in here. So we have this adjacency list I'm working on. So adjacency list, notice it's the same location, clang dash wall adjacency list .c, and I'll just leave it a.out. So make that change. Haha, this is why we compile a lot, because it's really easy to even forget a semicolon. And this is from void star. It really wants me to put the node t star, and we'll do the same down here for graph t. And also, this is going to be a node t star star. May not need it for the star star. We'll see. This is one of those, does my C remember correctly or not? All right, and we have all right. Aha. I said non-vertices, but I really should have been saying adjacency lists. And what I forgot to do was graph num-vertices equals num-vertices. So as you notice, no matter how much you're doing it, sometimes your code alongs can have mistakes, and that's all right. But you take a look at it, you see what's going on, you're probably sitting there in your end going, you know what, I saw that when I was coding and trying to figure out what on earth you're doing. Well, now you know, we debugged it. Most importantly, we compiled as we're going along. So yes, we have it. I'm going to go ahead and run it. Really doesn't do anything interesting, but what I'm really checking for is there going to be a memory leak or segmentation fault. So far, no. So that's a good sign that I have that. Once again, what I forgot is num-vertices should have been this, and then the adjacency list should have been that. It happens as we're coding along. Now, let's go ahead and say, all right, so we've got this structure. I want to add an edge to it. So I want to say void add edge, and it's going to be taking the graph. T, we're going to call it graph. We want the source edge, the location of where it's going, the first node, and the destination vertex, and we want the weight. Now we're going to say node T, new node, equals create node. And it's going to take the destination and the weight. And we're going to have to say, all right, is there an X in there? So we can say new node equals a new node next equals graph adjacency lists source equal is source. So what we're saying is, all right, so we have this next node. We're going to take whatever's currently in that list and put it as a next node. So instead of inserting at the end, we're inserting sort of at the front of this list. Doesn't matter what order they're in. So it's actually a really quick way to make every time we add a new node, we're setting at the front. Because now we can say graph adjacency lists source equals new node. There's other ways you could do it. You could have inserted at the end, but since order doesn't matter, it just matters they have the connected vertices for this instance, this is how we can go ahead and set it up. Then I can go ahead and come in here. And thinking about the graph I had, we can say, all right, add edge, and we had the graph. And then from location 0, we went to location 1, and we had 5 for the weight. So I can add that. Add edge, graph, and then from location 0 to location 2, we had 3 for the weight. And then add edge, graph, and then from location 1 to location 2, I put 2 for the weight. And then add edge, graph, and then from location 2 to location 3, we have 7 for the weight. And that helps us match. Let's go back to our graph real quick. That helps us match here. We have from 0 to 1, we had the 5, okay, and from 0 to 2, we had the 3. From 1 to 2, we had 2, and then from 2 to 3, we had 7. So it is matching for what we can expect, the 0 to 1, and we have a graph that was set up. Now it's not really useful unless we print it. So let's go ahead and print the graph, which means I'm going to have to build a function to print it. So often with the add and the print, they tend to be some of the first functions that we create. So I want to go ahead and print this graph. So void print graph, graph underscore t is graph. I'm going to say, all right, so I want to loop through this entire thing. So I equals 0, while I is less than graph, num vertices, I plus plus. And to make my life easier, I'm going to go ahead and just grab the current node. Technically, you could try doing this by using tons of pointers and the references and all that, but it's just easier to grab current equals graph, adjacency lists I, printf, and then if it's actually, if for any reason, current equals null, continue. We don't need to do anything else, just skip back, go to the next one. Theoretically, this shouldn't happen because we've got a completely filled matrix or a completely filled array for every vertice, and it's a one-to-one mapping. But let's say you built it so you had spaces or things like that. It's just a good check to have in there. And so while current does not equal null, actually, let's go ahead and print the current one. Printf adjacency list of vertex %d. Since we are using all things, then we can go ahead and say, yeah, let's put a space in there. Let's say I. And yes, technically we don't need the continue because this is safe how we're doing this because it is null safe, but the continue just means we skip that node or whatever we think that node is in there for some reason. So we can say printf %d, comma %d. I'll go ahead and do the space in there, and it is current vertex and current weight. And then of course we want to increment current, so current equals current next. So we've got this iterator pattern, and then at the very end, printf, we're just going to do \n. Technically, the very end is actually pointing towards null, so maybe we'll say null, just to make it very clear that the very end of this list is always points towards null. But really, often you're printing, leave off the null and just say, hey, that's end. But since we've got that arrow, we can go through and take a look at that. And we have the print graph, Okay, looks like we have everything. Do we need any extra? Nope, because I've got that there. It will always print it extra. So let's go ahead and save this. We'll find out if I have any typos or things like that, and that happens. And now let's run it. There we go. So we said from 0 we had 2 to 3, and then we also had a 1 to 5. Okay. Well, 1 costs 5, and then 2 costs 3. And then we have the 2 and the 3. Notice this is in backwards order from where we added it. So the first one I added was vertex 1 with a cost of 5. Second one I added is a 2 to 3 because we're adding to the front for efficiency. Could be adding to the end, but it saves time to add to the front as we have that. I'll go ahead and clear it and then run it again just so you can see the whole thing up above. And this only has a 1 edge, and this has a 1 edge. So I have built an adjacency list. Technically, it's now built. You said you can do it. But it's a lot more interesting if we can look at a distance. So let's go ahead and build a function that if I give it the nodes, it will tell me the distance between those nodes. I'm not trying to calculate the shortest path or any of that. I just want to say, here's a group of nodes, calculate the distance for me. So we can do int path distance graph t graph. We're going to say int star path, which says, hey, here's a path of items, and int path length, just to make our life easier by putting that on in. And the idea behind this is going to return the distance. So let's go and say int distance equals 0 to start off with, and we're going to return that distance. We also may need to go through the whole thing, but let's take a look. So now we can say for int I equals 0, while I is less than path length, I'm going to say -1. And the reason why is I always, when I want to look at a path, I want to look at 2 items. I want to look at the first item and the second item. By doing -1, I don't accidentally go over. I could start at 1 and just look at path length, but starting at 0 to -1 just seems to make a bit more sense in my head and how I try to plan it out. But it's different ways on how you can take a look at it. But it allows you to look, say we're going to be looking at 2 nodes at a time. So int source equals path I, so the source vertex, and destination equals path I plus 1. This is where this -1 matters, I do plus 1. If I did it the other way where I started at 1 and I went to path, then it would be I -1 and I. So it just sort of depends on how you set this up, but this tends to be a bit easier in my head. I want to get the current node, so node T is current node equals graph, and it's going to be, once again, our adjacency lists source. Now I'm going to be nice and sort of assume that the source is there and that I'm giving a valid path. It would be a couple more checks in here just to make sure that it was a valid path, but we're going to go ahead and do it this way. Sign equal null. Then we can go ahead and say if current vertex equals destination. So we're grabbing this, we're looping through until we find the destination. We can say, hey, look, we found it. In fact, I'm going to go ahead and print that we found it. Found path. %d, comma %d with weight. %d, period. And the 3 things I can go ahead and pull in is my source, my destination, and then current weight. And then my distance calculation is going to be plus equals current weight. Now the nice thing is once I've found it, and we're only adding these nodes once, I don't have to keep looping. So I can just break. I'm done with the loop. It's done. Let's get out of here. However, if I don't find it, current needs to be current needs to be current next. So I haven't found it, and I need to go ahead and toss it out. Now, if for any reason current node does equal null, I probably should print an error saying, hey, there's an issue with the path. So we'll go ahead and say printf error path %d %d. Not found in graph \n, And since they're trying to give me something that doesn't exist, we're just going to return -1 because it's distances and we were trying to be positive distances. We're trying to say, hey, there is no distance between this. At the very end, return distance, which I actually think I already had. So let's put that in the right spot. Notice a few things as it's coding this. By adding in the distance, I just saved myself from an error. I have my loop that's coming through here. I say if at any point current was never found, then I'm going to return a distance. I could also have this check up above or however we want to do it, but I'm just going to say it's an error. I can go ahead and put a comma in here just so it matches for the paths that I'm connecting, that they're always matching. So let's go ahead and compile. Make sure I typed everything out all right. We have that. And by the way, for not having to type it out, if you hit up on your terminal, it does that. Let me run it. All right, that's great. I haven't actually called this function. That would be helpful. So if I want to go ahead and call this function, we'll go ahead and say printf total distance and we'll pass in the path distance. It's going to be graph, and we're going to build an array on the fly by saying int, and we'll go ahead and say 0, 2, 3, and we know this array has length 3, so we're building this array on the fly. It'll be passed on in, it'll come out, it's on the stack, so once it pops off the stack, it will go ahead and be cleaned up on there, and then we can go ahead and run this. All right, let's go ahead and make our life easier. We'll go ahead and add a \n in here so we can read this easier. All right, so what we said is, all right, so we have from vertex 0, we went from 2 to 3 with a weight of 3. That's there. And then from vertex 2, we ended up wanting to go to vertex 3. So here's vertex 2 going to vertex 3, and that's weight of 7. When we combine the two, we have 10. Going back to our other graph, we go ahead and take a look at the graph that we have. We are coming in from the vertex. So we can come in here and we can go ahead and say, all right, we want to come from vertex 0 to vertex 2, and the weight is 3. And we want to go from 2 to 3, and the weight is 7, which of course does equal 10. And I may run this with a few other things to test it out, but in the end, we have managed to create an adjacency list, adding the various edges to it and building the graph. Now it is common, even though we use an array, it is common to use a hash table. When you use a hash table, some of these checks for null become a lot more important, and you're having to figure out how to get your keys from the hash table or things like that. It is used, it's not required. I mean, it's just sort of how you want to set up this idea for an adjacency list. But in this case, we happen to know the edges. It's within a small amount, so it worked well to use an array. You create your node or your edge, whatever you want to call this. You create your graph, and then of course you have your create. Always remember to write your free. Whenever you create something, your free malloc should, or your free should match up with your type of mallocs you have. Add your edge, and that's an important part for the adjacency list because it's actually a list of edges. And then you print your graph, and you can also take a look at your distance to make sure you're getting the right distance. Now notice this is being passed in. Later, when we look at things like Dijkstra's algorithm or things like that, you can figure out how to calculate the distance or calculate the shortest path. Calculating the shortest path on large graphs becomes a really hard problem. And that is something to really explore later in the future. It's not something that you are going to cover or even code very quickly, but it is something to think about, because let's take it into account if you are a UPS driver and you have this graph and all these connected locations and you want to reduce and find the shorter path by 30 minutes. Not so bad if you're in a small town, but now go worldwide UPS. Imagine if every route was reduced by 30 minutes. Imagine how much fuel and time that you would save and how much of an impact that can have on the world around us or even the environment around us. So these problems have real world applications especially when we start getting into graphs and looking at graphs and figuring out the distance between edges and mapping things to these graphs that are fundamental problems today. So as always, I encourage you to keep coding, keep practicing, and have a wonderful day. Happy coding.